The earlier lecture, we have already learned that how we can design the pedestals and the reinforcement as per AS statistics under 2018. Now in this lecture, we shall learn that how we can design the concrete foundations for this kind of structures. So considering that, let us assume that we do need concrete pads, that is rectangular concrete foundations for these. So to design them, we shall need the horizontal reactions along both the axes, the vertical load that is coming on the foundation, and the most important, the bending moment that is coming along both the axes, that is along the x-axis and y-axis. So for that, what we can do is that, let us say we can go to the support and spring reactions here. So in here, let us say we switch on these fx, fy, fz, mx and my, because mz shall be torsion on the foundation, that we are least concerned for these kind of structures. So we can left click on apply here. So here you can see that by clicking on the tabulated, so these are the horizontal reactions that are coming for this particular, let us say, load case. That is the serviceability 0.9 dead load plus 1 time wind load by service. Now the thing is that what we should do is that we do need to design the foundation. Approximately how the foundation design is done is that we do ensure that whatever bending moment and whatever axial load is coming, their interaction, whatever is the bearing pressure that is coming, that should be less than the bearing capacity. So what we can do is that we can go to the display and show tables here. And in here, we can go to the joint output and click on the, we can say, joint reactions here. So here we can click on the joint reactions. We can like switch on the base only. And among the load combinations, we can select the dead load, live load, press Ctrl key on your keyboard, piping, and WLX and WLY. So we can like left click on apply multiple items filters. And let us say when we are like concerned only about this particular node, let us say if you want to design the concrete foundation for this particular node, that is 170, we can select this node and then press Ctrl T option on your keyboard, and then repeat the same procedure here. Let us we go to the joint reactions, and we here select the load cases that are coming, that is the dead, live, piping, WLX and WLY. Left click on apply multiple items selected filters. So these are the like reactions that are coming, and we can like minimize this non-effective tables, and we can stretch the tables like this. So now we can see the reactions that are coming. We can just simply export the current table to Excel. Now after exporting these particular table to Excel, so we get these values here. We have done the switch off the precision. So these are the values that has been exported from the ETABS, but we like make them number round off. So now these are the reactions that are coming for this particular node, that is we can say 8 number and 170. Now the thing is that either we can directly derive the design from the, we can say, load combinations values, or we can derive each and every load case values again, and then we can design the foundations as per the ES statistic 100. Now, when we design the pedestals, and when we have already designed the pedestals, and when we design the concrete foundations for that, the foundation size that is coming is approximately, we can say, 4500 mm by 3500 mm, and we can say that the length of the pad footing, that is okay, 4500 by 3500. Area is nothing but 4.5 into 13.5, that gives us value of 15.75. And the thickness of the foundation, the thickness that we have considered for this particular foundation, that is approximately 750 mm. And the height of the soil above the footing, that is also considered as 750. So in total, we can say that the footing bottom is approximately 1500 mm from the natural ground level. And the pedestal that is coming here, This dimension is approximately, we can say, 1000 mm, and this dimension is approximately, we can say, 800 mm. Density of the soil, we can assume it as 20 kN per meter cube. Shear strength, that is approximately 25 degree, phi dash, and design base friction, that is assumed as approximately 19.3 degrees Celsius, degrees. And ultimate design bearing capacity, that has been considered as 225 kN per meter square. So this is, we can say, bearing pressure, and that is usually given by the soil consultant, or we can say geotechnical consultant. And that is the job of, we can say, geotechnical consultant. We don't need to, go into the detail of that, but that is usually given as an input only. Now these are the load factors for stability. So for stabilizing, it is 0.9. For destabilizing, it is 1.35. And for imposed load factor for destabilizing, it is 1.5. And for destabilizing, it is 1. Now the axial loading on the column for the dead, imposed, and wind. Now imposed is considered as live, the live load plus piping load. So there's a difference in terminology that has been given here. So the dead load is basically the self weight, that is approximately 101 kilonewton. Dead live load plus piping load, that is given as approximately 478 kilonewton. That is derived from the ETABS only. And wind load, vertical load, that is coming as approximately 177 kN. So in total, we can say that the total axial load on the column that is coming is approximately, we can say, gamma dg. Gamma dg can be referred from here, that is 1.35. And gamma dq is 1.5, that can be referred here. And pqa, that is already given here, plus gamma dw, that is the case of the wind, that is given as 1, and that is multiplied with this particular value. So in total, that gives us 1030.4 kilonewton. Now the surcharge load and post surcharge load, that has been assumed as 0 only. And pad footing self weight, that we can simply calculate that the thickness that is coming is 0.75 into, we can say, 25. That is a concrete density, so that gives us approximately 17.7. And soil self weight, that is nothing but, we can say, 20, that is density into height of the soil, that is 0.75. That gives us 15 kN per meter square. So in total foundation load, that is coming, we can say, 695.3. How we have calculated that? Again, we have used the same function here, that is gamma dg into this particular value and plus this particular value, both of them are 0, plus soil, that is 15, and that is multiplied with gamma dg plus gamma dq into sur, that is 0 only, because we have considered surcharge load as 0. So that gives us 695.3 kilonewton. So horizontal loading on the column base. Now obviously, when we're talking about the foundation, any kind of foundation design, so let us say this is an isometric view of the foundation that we are right now discussing, and this is the pedestal on the top. So what we can see here is that, let us say this is the vertical load, this is the bending moment. Now the bending moment, they can be there for both the axes, that is for this axis also and for this axis also, and axial loading also. In addition to that, there shall be horizontal loading also, that is coming on this particular, we can say, point. Now that we have already calculated with the help of ETABS. So horizontal load, that can be simply referred from the Excel file that we have exported. So here we can see that it is approximately 2 kilonewton, that is dead. For live and piping, it is approximately 1 plus 59, that is 60. And for wind load, it is approximately 128. So that has been referred here, 128, 60, and 2. So in total, by multiplying it with gamma dg, the corresponding hga, gamma dq with corresponding hqa, plus gamma dw, that is 1 for wind, that gives us 220.7 kilonewton. Similarly for the y direction, so y direction 132 and 137 has been referred from here. So 1 and 26 plus 6 has been referred to 32, and 137 has been referred here. Now thing is that this and this, both of them are opposite direction, so it can be referred as 6 minus 26, that is 20 kilonewton also, but on the conservative side we assume that on the higher side only, that is 32. and wind horizontal loading in y direction 137. So that again by multiplying with corresponding gamma factors, that gives us 186.4 kilonewton. And moment on the column base. So when we're talking about the moment on the column base, so similarly, the values that we have calculated that with the help of an Excel file. So similarly, we have derived that 140 and 247 from the Excel itself. So here we can see 147 minus 740, and this here is 242. So that has been referred here. Similarly, multiplying with gamma dg, gamma dq, and gamma dw, that gives us 308.35. Similarly, for the moment in the y direction also. So considering moment in the y direction, it is, we can say, 3 and 91 and 195. So 391 and 195 gives us 335.55 km meter as the moment. Now, if we're talking about the check stability against the sliding, so the resistance to sliding due to base friction, that value is coming approximately 194.2 kilonewton. And passive pressure coefficient, that is nothing but 1 minus plus sine phi divided by 1 minus sine phi, that gives us 2.464 as the value. Now this phi dash value that we have already assumed here on the top as 25 degrees, and that is usually given by the soil consultant itself. Now the thing is that we do need to calculate the stability against the sliding. Now if we want to calculate the stability against the sliding force that is coming here is approximately, we can say, HYA square plus HXA square and square root of the number that is coming. So if we are talking about the HYA 186.4 and HXA is 220.7 kilonewton, and we add them, add them, and we take the square root of them, that gives us 288.9 kilonewton. Now the resultant force angle is nothing but in a tan inverse of this is A tan, that is tan inverse of HYA divided by HXA, that gives us 40.18 degree. So passive resistance of soil in X direction, that is 0.5 into gamma Sg into Kp, the value that we have calculated here, and multiplied with H square plus 2H into H soil multiplied with P multiplied with density of the soil. That gives us 131 kilonewton as the passive resistance of soil in X. Similarly, we can calculate the passive resistance of soil in the Y direction as 168.4 kilonewton. So resultant passive resistance is absolute value of Hx into cos alpha plus absolute value of Hy into sine alpha. That gives us 208.7. So total resistance to sliding, that is nothing but we can say H friction, that is 194.2 kilonewton, that is given here, plus 208.7. So that gives us 402.9 kilonewton. Now the thing is that if we want to calculate factor of safety against the sliding, so that is basically 402.9, that is the capacity, divided by the HD, that is the resultant force that is coming here, that is 288.9. So 402.9 divided by 288.9 gives us 1.395. So resistance of sliding is greater than the resultant horizontal load. Similarly, we can calculate the stability against the overturning also in both the directions. So overturning moment in X, that can be calculated here, and restoring moment in X direction, that is the basically the parameter of the soil itself, that is there. So gamma Sg into FGSUR, such as that is 0 here, self weight, and we can say the soil weight multiplied with A into L by 2. So that is basically the foundation loading, and axial loading, that is this particular value, restoring moment is this particular value. So the factor of safety against overturning is nothing but 1247.45 divided by absolute of, we can say, MXOT, that is this particular value. So that gives us 2.632. Similarly, we can calculate the factor of safety against the y direction. Now the important thing, or the important parameters, is this particular graph here. Now this is very important that you do need to understand what exactly are we talking about. So the foundation and the soil interact in a very easy way, we can say. Let us say whatever load is coming, the soil shall be exerting pressure here. Let us say there is a bending moment also, so there shall be, we can say, a graph something like this. So here there shall be a little bit of higher bearing pressure, here there shall be a little bit of lower bearing pressure. Let us say this axial load is very less and this bending moment is very high. So in that particular case, this graph may go something like this also. So in that case, we can say that footing is in tension. So to avoid that, what we do is that either we increase the thickness of the footing or either we increase the depth of the foundation so that the soil itself acts as a restoring for this particular case. Now, in any case, the bearing pressure and bearing capacity, these are the two different terms in which we do need to be clear before we proceed further. That is a bearing pressure and bearing capacity. Now, the rule that we do need to always remember is that bearing pressure should always be, we can say, less than the bearing capacity. Only then the foundation is safe. So in our case, the bearing capacity value, that is approximately 225 kilonewton per meter square. So let us say the bearing pressure that are coming. Here we can see that on this particular edge, the maximum bearing pressure is 121. On this particular edge, it is 201.4. And on this particular part, it is approximately, we can say, 97.9. And on this particular part, it is only 17.7. So we can say that this 201.4, that is less than 225 kilonewton per meter square. So our foundation is safe. Now, the second aspect is that we should always, try to understand how these values have been calculated. So here we can find out this particular value here is 201.4. That is what we have done here is that T by A plus this particular formula plus this particular formula. Now this formula may look a little bit of complicated, but the simple formula that you do need to understand here is that is P by A plus minus mx by zx plus minus my by zy. Now the z here is nothing but b into d square by 6. That is a sectional modulus, or it is also known as second moment of area. Now this bd square by 6, here we can see this 6 has been calculated here. And if you're talking about let us say b into d, now this is the area, that is A is already has b into d, and again it is multiplied by b. So that is how we can calculate that. And this T into E, this value is nothing but the bending moment that is coming here. So what we have done here is that here you can see minus 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 plus plus minus and plus and plus. So that is how we do have 4 cases here, that is plus minus and plus minus. So by doing that, this is how you can calculate that the bearing pressure that is coming. So the minimum is approximately 17.7 and maximum is 201.4. Why minimum is important? It is because it should not be in tension. So we can say that maximum base pressure is less than the ultimate design bearing capacity. Now the load factors for design. What now we are designing here is that we have now calculated the size of the foundation that is safe, and it is the pressure is less than the bearing capacity. Now we do need to calculate the reinforcement also that we do need to put in our foundation. So reinforcement in our case, that is like quite simple. Let us say this is the foundation that is coming here. So we do have a reinforcement along this axis and we do have a reinforcement along the other axis also. So whatever, the bending moment that is coming along the, we can say, x-axis. So whatever bending moment is coming here, this reinforcement shall take the part, and whatever bending moment is coming along this particular direction, this reinforcement shall be contributing to the strength. So that also we shall check that what exactly is the reinforcement requirement. So coming back, these are the load factors, that is 1.4, 1.5 and 1. So ultimate axial loading on the column is 103.0.4 and ultimate foundation load that is coming is 695.3. These are the ultimate horizontal loads and these are the ultimate bending moments. So ultimate pad reaction that is coming is, we can say, approximately 1725.6. So ultimate pad pressures are, we can say, 201, again the same value, that is 201.415. So rate of change of base pressure, that also we can calculate with the help of the simple formula. Pad length in x direction, this is basically nothing but half of this particular number. So this direction was 4.5, so this is approximately 2250. Ultimate bending moment that can be calculated here, that is again a very simple formula, or again a simple concept. we do assume that there is a bending moment that is coming here. So we do know that, let us say there is this fixed support here, and let us say there is this UDL that is coming. So the bending moment at the end is W into L square by 2. Let us say this is the uniformly distributed load W, and this is the cantilever span L. Same has been considered here. That is FUL, that is basically the UDL that is coming on the bot from the bottom to the top. L is here is 2250. And after that, what we can see here is that we have calculated the bending moment, the contribution for the bending moments also. So this is how we can calculate that. After that material characteristic, we can assume that, let us say the grade of concrete is 40 MPa. The Curtis time, the strength of reinforcement is 500 MPa. Cover has been considered as 50 mm. So moment design in X direction, we can say that diameter of, let us say, tension reinforcement has been assumed as 20. So providing a T number of 20 bars, the spacing comes out to be approximately 200 mm center to center. So the distance between two bars is approximately 200 mm here. So area of tension reinforcement provided, that is nothing but number of bars 18 into area of one bar, that is pi into diameter of bar square divided by 4. So that gives us 5655. Depth of the tension reinforcement. Now this depth here is 750 mm. The cover is 50 mm, so that gives us 700 minus the half the diameter of the bar, that is 20 divided by 2, that is 10. So that gives us 690 mm. And minimum area of tension reinforcement as per clause 21.3.1 is 0.114 into B into H square into square root of FC dash and divided by FSY into dx. So that gives us 4114 mm square. So the tension reinforcement provided exceeds the minimum tension reinforcement required. After that, if we're talking about the compressive stress factor and compression block depth factor and neutral axis factor. So these are the standard formulae. That is alpha 2 value is maximum of 0.67 or 0.85 minus 0.0015 FC dash or 1 MPa. So that gives us 0.790. Compression block depth factor, that is the gamma, that is maximum 0.67 or 0.97 minus 0.0025 into FC dash or 1 MPa. That gives us again 0.87. So after the neutral axis parameter, that is KUX, that can be calculated by multiplying area of steel into the yield strength of steel divided by alpha 2, that is this particular value, gamma, that is the density, FC dash we know 40 into B into dx. So that gives us 0.043. So neutral axis parameter is less than 0.36. After that, if you're talking about the capacity reduction factors, so that is again the maximum 0.65 or minimum of 0.85, 1.24 minus 13 into KUX divided by 12. So that gives us this particular value, that is 0.85. So design bending moment comes out to be 816.509. And moment capacity of the base that is coming is 1627.57 kilonewton meter. So moment capacity of base exceeds the nominal moment strength required. So this is how we can calculate the area of steel requirement for the, we can say, foundation. After that, if you're talking about the moment direction in the y direction, the same calculations that we can follow in the y direction also. That is compressive stress factor alpha 2 gamma. So the neutral axis, the parameter comes out to 0.0034, which is less than 0.36. Capacity reduction factor is 0.85. So the design bending moment is this, and the capacity comes out to be 1586.33. So after that, the shear parameter also, that also we do need to check thoroughly. So if you're talking about the shear parameter, here you can see that ultimate punching shear parameter has been checked. And here we can see the shear strength at distance d from the face of the wall. That is also known as one-way shear. So that has also been checked here. So ultimate pressure for shear, that has been calculated by putting these values as 140.231. Area loaded is 3.71 meters square. Ultimate shear force that is coming is 356. Effective shear depth, that is 0.72 into h or 0.9 into dx. And minimum area of shear reinforcement is 1011.9. And KDG value 0.89. So web crushing limit has been calculated as 36 degree. So let us say this is the force, and there is this crushing angle. So this theta that has been calculated as 36 degree, and crushing limit has been calculated as 20464.5 kilonewton. So that is much higher than the shear force that we are talking about here. So shear is within the web crushing limit. Similarly, if we're talking about the shear distance d from the face of the wall, so shear strength reduction factor is 0.7, and longitudinal strain in concrete at mid depth that can be calculated here is 0.00074. So design shear strength with no reinforcement is 1064.8. So no shear reinforcement is required. After that, similarly, we can calculate the ultimate punching shear force also at d by 2 from the face of the column. So ultimate pressure for punching shear is 109.564 kN per meter square. Again, the effective depth is 680. Area loaded for punching shear is 2.486. Length of the punching shear parameter is 6320. And ultimate shear force at shear parameter is 867. And the capacity, if you're talking about the capacity, that is much higher. Here we can see that concrete shear strength is approximately 3918, and concrete shear strength with no, we can say, moment, that is much higher, that is 6468.37. So in total we can say that the reinforcement that we are provided is safe for the bending also and for the shear also, and the sizing of the foundation that is also safe considering the bearing pressure that is coming. So that is how we can design the foundation also for the pipe racks.